It is my pleasure to welcome you to this third talk in this spring series of our California Water Colloquium. Before I introduce the speaker, I just want to make couple of quick announcements. One is that we are sending out a little clipboard here. Please, all of you, please sign your name on this so that we can have the number of people and the people who are attending this colloquium. And there is a last column here which is optional. If you want you to be reminded by email about the future colloquia, please put down your email address and we will inform you by email. And here we have a few brochures which is telling about this colloquium, so Linda will have them with her. If any of you want, please ask Linda for them. Today we have a very distinguished civil engineer who has done for almost 50 years or more, who has served California and the nation in a very distinguished way about groundwater education as well as managing groundwater. Professor David Todd taught civil engineering, especially hydrology, surface water hydrology and groundwater hydrology for many years during the 50s until the 70s, when he decided that he had done enough of teaching and he wanted to dedicate his service to the profession. So he retired rather early in his career, and since then he has devoted over 20 years to consulting, and he has served the country extremely well as a consulting engineer. He has brought great distinction to the profession. Perhaps Professor Todd is best known for his, in 1959, he published his first edition of his textbook, Groundwater Hydrology. Probably the first definitive work on groundwater hydrology, which dealt with quantitative and engineering aspects. Prior to that, we had some books on groundwater which are more descriptive in nature. And that book has, in the last 43, 44 years, it has become a standard in the profession. It is being republished in several editions. It has been translated into many languages: Hindi, Portuguese, Malaysian, Turkish, and what have you, many languages. And I myself have used that book. It is extraordinarily meticulous in its detail. And Professor Todd's work has always been distinguished by very thoughtful, very precise, very meticulous work. And today it is a great pleasure for us to invite you back to Berkeley and talk to us about the very general topic of groundwater management. It is a very profoundly important topic in California, and I cannot think of anybody better suited to talk about it than Professor Todd, who has spent nearly half a century dedicated to the profession. Professor Todd.
This looks like a news conference with all of these things sitting up here. I'm very happy to be here, and I want to first of all say thank you to the Water Resources Center Archives because not only for inviting me, but also for the fact that the archives over the years has been probably the most important single resource in my professional career. And as a result of that, it has achieved an importance in terms of my life that I think is to be remembered by everyone. And to Linda Vita, who is here running this operation now, she has done more to enhance and develop and improve the archives than any time that I have known it in the history. And any of you who are not familiar with it certainly should become familiar with it, because it is one of the great facilities that we have here on the Berkeley campus, and one of the reasons that Berkeley is the great campus that it is today. In groundwater management, that's a wide open subject if you stop and think about it. And what I'm trying to think how to start on something like this, the best way would be to focus on the fact that we're dealing with what I would call a virtual resource. The word virtual is getting a lot of use these days. Recently I was reading the book Paris to the Moon by Adam Gopnik, and he was commenting on the modern culture scene that we're in. And the difficulties that he was pointing out is that so many things are, but they aren't. The word virtual is sort of hard to define sometime, but it really represents something that is and isn't. For example, you say that a certain person is a virtual dictator. That means that he is a dictator, but he isn't a dictator. And it's that kind of thing, whether it's communications or travel or anything else that's going on. There's a virtuality that's in our modern resources. And that same thing, I think, applies to groundwater, because I think you can talk about groundwater as a virtual resource, because it's all around us, and yet it's not, because we can't see it and get our hands on it. For example, this room is, what, 40 by 50 feet, let's say 2,000 square feet. If we have underneath us 100 feet of saturated soil thickness with a 20% porosity, that's 200,000 times 0.2 is 40,000 multiplied by 7.5. That's a little over 300,000 gallons of water sitting right under this room. In other words, literally 1/3 of a million gallons is directly below us right here, slowly drifting here to the west. So this is what I mean about a virtual resource, because it's around us, but it's not around us. The subject of groundwater has received a lot more importance in the last few years, particularly, as was just mentioned, because of the fact that it's become the available resource. We have in this state something like 170 million acre-feet of groundwater, fresh groundwater that's available. We have, in terms of groundwater storage, in all the reservoirs we have in California, a little over 10 million acre-feet of water. So we got a 17-to-1 ratio there. So that the groundwater is important not only volumetrically, but also because, unfortunately, surface water is literally not available anymore, because the best dam sites are gone, new dams are very costly, and environmental concerns that we think are very important today preclude development of any major surface water. So the whole concept of development of groundwater has expanded tremendously, and the focus really that I want to talk about is ways of managing groundwater, and that also means mismanagement of groundwater in terms of the ways it can be done, how it can be done, and give you a few examples of actual situations. I think of a groundwater basin as a large pool of water, and the easiest way to think of it is basically as a relationship to a surface water reservoir. You take something like Shasta Dam. You have a beautiful large dam on the Sacramento River, and what you have is a large storage water back of it. The advantages of that dam is not to keep it full of water all the time, because if you do keep it full, the benefits that you get in terms of hydropower, flood control, water supply, and so on are not available, because you're simply taking the run of the river water that's coming to you. By the same token, we don't want to keep it empty all the time. That doesn't serve any purpose. We've got a lot of flood protection, but we don't have anything else. So the advantage is of course, the storage. You've got to be able to move the water level in the dam up and down, back and forth. Well, that same concept is basically what we're talking about in groundwater, if you think of groundwater as a reservoir. Again, it's virtual because you can't see it, you can't get your hands on it, it's difficult to define. Three-dimensionally, I've often thought about how you define a groundwater reservoir. You think of something that, let's say in a valley or a river basin, it may be tens of miles across and it may be a couple hundred feet thick. So what we have in 3 dimensions is a very great big flat pancake. Actually, a pancake is probably too thick. We probably better make it a crepe to get it down to a size that would actually fit. So in something like that, the management becomes fairly difficult because it's unwieldy. I mean, how do you get at this whole great big flat mass that you're dealing with? The secret, of course, here is that we're working with the water level, because the storage is what we have to work with here, the same as in Shasta Dam. So your water levels in a groundwater area, well, there are a lot of different factors, but groundwater levels are moving. All groundwater is moving all the time, very slowly, granted, but nevertheless it's moving. And so the water levels fluctuate up and down, and if we can control those fluctuations, we can take advantage of the storage just as you do in Shasta Dam. Now, water levels in typical groundwater situation go up and down, first of all, every season. It rains in the winter, it's dry in the summer. The heavy pumping for irrigation, which is 80% of the pumpage here in the state, is in the summertime. So your water levels go up, high in April right now. They go down to about October in the fall, and then they start back up again. So you have this zigzag sine curve going across there. You have that every place in the state to a smaller extent, maybe a few feet up, a few feet down. In addition to that, however, you have a lot of them where the zigzag is just like this, but it's going like this. And those are overdraft situations where we're taking more water out than we have coming in. And we have places of that sort in Southern California. We have lots of it in Arizona, other locations where we're simply taking more water out than is coming in, so the zigzags are skidding downhill to hopefully some sort of a stabilized position going through there in the future. But the biggest problem in something like this is to maintain this water level within certain limits, an upper limit and a lower limit. For a dam and a dam site, obviously we know the upper and lower limits very well. For groundwater, the lower limit may be controlled by geology, because we would never pump an aquifer completely dry to get the last drop of water, but usually it's controlled by the permeability, where the best permeability is, and also the ability to pull the water level down to a point where you can still get at it with wells. So it depends upon the depth of the wells, which are usually controlled by the permeability, the structure of the aquifer, and as a result of that, this water then moves up and down to that level. So the lower level is the control in terms of availability. The upper limit, of course, depends on local conditions, but typically you don't want to get too close to ground surface. If you do, first of all, you get saturation. The root zone becomes saturated in there. You have evaporation of water going out from this. You'll have soggy conditions in urban areas. You'll have waters in the subways, or you name it. There have been lots of problems in dewatering of subways in Brooklyn for years and years and years. They simply can't stop it all because the water table is too high right close to the ocean. So these are the problems they're dealing with. Is an upper limit, which is a practical one. There's a lower limit that's a practical one that's involved in it. Now, an illustration of where we don't have management or have not had management, but it makes common sense in terms of what we're talking about, is a situation in the Indus Basin in Pakistan. Let me just make a sketch. The Indus River has 4 tributaries and the main stem itself, so there are 5 rivers coming down. In Urdu, that stands for the area of the Punjab. Punj is 5, Ab is river, the land of the 5 rivers. In between each one of these is irrigated land. There are something like 25 million acres of land in the Indus Basin at the present time. Most of it is irrigated. And each one of these is supplied by canals coming into this area, so that what you have then is water being brought in from the adjacent rivers. Each one of these is a doab, 2 rivers. So you have a doab and a doab and a doab, but the whole thing makes a punjab when you put it all together. What happened there is that irrigation was developed in the middle of the 19th century. The British were involved very much in that when it was India, of course, a long time ago. And with the development there, that became one of the largest irrigated areas in the world. It's a very flat area, very permeable, and it slopes all the way down very, very gradually down to the sea at Karachi. The problem was that with all of the diversification of water going in, what you have is water being brought into all these different areas, out through them, all over the area, so that you start with big canals and smaller canals and finally little field ditches. It was all done just with surface construction done by hand labor, and as a result, why all of this area then became sort of a great big well, I guess you'd just say a sort of a sieve, water dripping down through there. As a result of this water being brought in, of course, a lot of that water was not used for irrigation, just simply soaked into the ground. It went down to the water table. The water table gradually rose, about a foot a year, actually, historically we know. And so from 1850 up to 1950, the water table suddenly came up almost to ground surface. So now you had a situation where you had a water table, which actually would be visible in low points in there. You have saturated soils, you have evaporation, you have salt accumulation in the root zone, and flying over the area, you could even see white, looks like snow, simply because of the salt crust that was beginning to form. Clearly, this represents a major destruction of agriculture, which is the #1 product for the country of Pakistan. And so the main thing was, how do you manage this? Well, the solution here is to obviously get the water table down. And so what was developed in this particular area was to put in a grid of wells all over, just literally a grid of wells all over, going down into there, maybe 150 feet deep was all that was needed. And so each one of these, of course, has a dimple around its well, but together the whole thing is pulled down in there. As a result of that, you then have all this extra water coming in. You put it on the fields so that you over-irrigate the area. With the water table down, you have this fresh water coming up because this is good water below. Put it on top and it washes the salts down. And as a result, by keeping the water table down, maybe only 10 or 20 feet is all you need to do it. It doesn't have to go down forever. Then what you're doing is flushing out the root zone in there and maintaining good quality water and keeping the irrigation system going. One of the basic concepts of groundwater management is what we call conjunctive use. It's a term that's widely used and a very simple concept, and it works very well. By conjunctive use, we mean simply surface water and groundwater used in conjunction with each other. So that the simplest way of stating is, if we have a wet year with lots of extra water, we use all the surface water we have because we have it available there, and the surplus water, we put it into pits or basins or little shallow troughs of some one type or another, and let it percolate down so that you're increasing the amount of water that's going into storage. We speak of that as artificial recharge, as contrasted with natural recharge, which is just rainwater dripping into the ground. So by getting this water into the ground, you therefore can build up the groundwater resources. With that, then, in a dry season, when you have a shortage of surface water, you have water in storage. It's like money in the bank. You can then pump it out and make use of it. So again, what you're doing is filling it up, taking it down, and here's your storage of water moving up and down within the limits we just talked about. That concept is very widely used throughout the state. The Department of Water Resources in Sacramento has listed more than 200 artificial recharge projects in this state alone. So it's something that's used not often on a large scale, sometimes very small ponds and things like that, but at other times it's a fairly large one. The best illustrations I can think of, which you may know something about, is Santa Clara County down in the San Jose area. All the water that drains into that area is usually collected into ponds or lakes or something like that. Often there's water skiing on them and things of this sort where they can be used recreationally, but they all leak. And that water is going down, and so you put as much water into storage as you can rather than letting it run off and be wasted. Another good example is in Orange County Water District, down in the area of Anaheim, Newport Beach, that area. That area all depends upon water from the Santa Ana River. The Santa Ana River drains from the San Bernardino area, comes down into this area, and once it gets down there, it, of course, is wasted into the sea. Well, this is the main source of water, and so to catch that, what the Orange County Water District has done over the last 30 or 40 years, it was one of the first ones, as far as I know, to do this in California. They began to put in small ponds along the river. They took gravel out of the river so they could make deeper ponds in the river itself. They took old gravel pits that were nearby and brought water and put them in there also. And so the idea is to take all the water you can and let almost none be wasted into the ocean, to put it into the underground to build up your water supply. And so again, where in 1950s, the water table was very low in Orange County because of the heavy pumping that had gone on in the post-war period, and as a result, everything was down low. With this development that was brought into effect after that time, suddenly this area has been filled up, and now we have a pretty good equilibrium in terms of water in and water out. Another example of that that's going on right now is with regard to places like in Southern California, the Metropolitan Water District. The Metropolitan Water District is the wholesaler of water, has a contract with the state of California to deliver water into Southern California urban areas. They serve some 50 or 60 retailers of water throughout the state in the southern area. The problem here, of course, for Southern California is the usual one in terms of demand is outstripping supply. We have a lot more people than we did 100 years ago, and yet we've only got the same amount of water still here. So what's happened here is that, of course, the Los Angeles area brings in water from every place they can get their hands on it. There's local groundwater, there's local surface water, there's water from Owens Valley, there's water from the Feather River, there's water from the Colorado River. All of these are sort of a spider web bringing water into the Los Angeles area. But the demand is still there, and again, for the drought periods, and we keep thinking about the droughts of the 77, 78 period and the 90, 92 period that we had here in California, and we begin to worry about, are we going to make it? Because the population curve is still going up. We've gone from 34 million right now, as I understand the figure is. We're talking about 50 million, almost a 50% increase in the next 18 years up to 2020. So what can be done about it? Well, there fortunately are aquifers with space available, storage space, and the beauty of groundwater aquifers is that there are reservoirs that are waiting to be used, that are already constructed, and you can put them to immediate use. So the Colorado Aqueduct, bringing water in from the Colorado River, winding across the Mojave Desert, coming into Los Angeles, is now going to be short-stopped, as it were, along the way. And what's being done at 3 different locations. One is called Cadiz, one is called Hayfield, and one is called Chuckwalla, after the little lizard. And each one of these is going to be used to develop water by putting it underground, so that if you have, for example, an aqueduct, it may either be a pipeline or a canal, bringing water in around a certain area. On the downstream side, where it makes a bend around someplace, you'll divert water out of the aqueduct, have shallow basins, maybe 50 or 100 acres, great big areas, just put water into it, let it soak into the ground, and go down and build up the groundwater supply. And that water then can be picked up by a line of wells on downstream from where the basins are and put back into the aqueduct in that dry year that we know is coming at some time in the future. So this concept is receiving a lot of attention, and it is just direct applications of what we call conjunctive use in terms of trying to apply something like that. Another thing that's happening is in the groundwater management area are transfers. There is, of course, a great interest now in transferring water from, let's say, a wet area to a dry area. And the typical thing would be taking water that somebody is not using or is willing to sell, let's say in the Sacramento Valley, and bringing it down to the Southern California and making it available for people in the San Joaquin Valley. This involves transport, which involves the state of California. It involves costs. It involves clearances and a lot of different things. It isn't just as simple, but it can be done. And we can do the same thing indirectly with groundwater. For example, if you have a basin or something like that, you can pump water here at various locations where wells are located, or you can change that arrangement depending upon what you want and where you want the water. A simple illustration that I can think of on that is the one at the Mojave Water Agency, which is down in the vicinity of Apple Valley, where you have a very large aquifer, even though it's a very dry area. And each one of the farmers or ranchers can sell 50 acre-feet of water a year if they wish to. So if somebody isn't going to be growing apples or tomatoes or whatever it may be in a particular year, they can sell 50 acre-feet of water for a fairly good price. And somebody 2 miles away says, well, I need that additional water this year because of something I'm doing. And so he will turn off his pump and he will turn his on. So the water is moved around, it's delivered where you want it, there's no canals or anything involved. You're simply taking water, moving it from one point to another. So that kind of exchange transfer process is one that I think is going to continue to expand on into the future. Another example of groundwater storage is the one in Kern County. Kern County Water Agency operates what we call a Kern Water Bank. And the Kern Water Bank is nothing more than a pool of water right near Bakersfield that was set up by the state of California so that when, again, there was available water in wet years, this water was brought into these large flat basins and allowed to soak into the ground and build up a water supply. We now have this bank essentially full of water. It's as much as it can carry right now, and it represents an ongoing reserve which the state has wisely set aside to make sure that this water will be available at times in the future. John Muir once said, "When one tugs at a single thing in nature, he finds it attached to the rest of the world." I think that's a very nice statement because it applies so well, it seems to me, to groundwater. Because anytime you drill a single well, you're of course creating a dimple in the water table, and that dimple is going to spread out as you keep on pumping the well. It's like throwing a pebble into a pond. You get a lot of circles, but the circles keep on radiating outward. And so this hooking on to the rest of the world is one of the classic problems and situations that we run into in managing groundwater. A good example of that is described in a recent report by the Kansas Geological Survey. And this involves the Solomon River. Now, the Solomon River is a river of about 3,000 square miles, roughly, in western Kansas. Western Kansas is flat and relatively dry and very good soil. And what's happened there is that, of course, most of that area is developed for agriculture, for wheat and for corn. This is really the breadbasket of Middle America. And what's happened there in the last 50 years is two things. First of all, irrigation development has come into this area. And with the development of what we call center pivots, these big circular circles of land, if you've flown an airplane, you see pretty green circles underneath. These are center pivots. The water is coming in automatically distributed by a self-operating sprinkler system that goes around in the area. What you're doing, of course, is taking water from the ground because the river itself is narrow and small and incised. Thank you very much. Is incised, and there is not enough water to be developed in the area. And of course, the demand for groundwater is very large. So as a result, all of these center pivot operations are going all over the area and taking water out. As a result, the groundwater table is going down. The second thing is that there's, of course, the majority of the area is non-irrigated. Probably, I'm estimating more than 2/3 would be non-irrigated as compared to irrigated because of the costs. And so in the non-irrigated areas, what happens here with the help of the Soil Conservation Service and lots of advice from the federal government and state government is to conserve water as much as possible. And so what a farmer wants to do there is to keep water on his land. And so what you do is to go in on the field, which has a gentle slope, whatever it may be, and you put it into a series of very shallow flat terraces. You have to really look to see them. They're only a foot or two step down like this, and you walk along, so that when it rains, the water doesn't just run right off of the surface. It sits in these little ponds and soaks into the ground the next day or two. So you have these little arcs of ponds of water sitting there in the terraces. At the same time, water that is draining off is often picked up by what are called tailwater ponds. Water that does run off is picked up and put in a little pond that can be constructed with a backhoe. And that water is collected. It can be used for cattle. It can be used for other supplemental irrigation if they have a pump on it, and make use of that water. The net effect of all this, of course, is that there's almost no water running off to the stream. So if you have no water running off to the stream and you're lowering the water table, and the water table obviously drains to the stream, which provides what we call the base flow, the basic flow that's coming out, what you're going to do is decrease the stream flow. And so the Solomon River today is now flowing, going down to Manhattan and Kansas City, which is where it's being used for urban purposes, has now an average flow of less than 50% of what it did 50 years ago. Now, there's no way to turn this off. I mean, you say, well, what's the management plan here? Well, there isn't any good management plan immediately available. You're not going to go in and tell farmers not to farm or kick them off of their fields or turn off their wells, but clearly it's going to take a very careful planned management, and part of it is political. It isn't all hydrologic. What you've got to do basically, and what is being done in these areas, is to develop local management districts, water resource management districts, which are with a group of intelligent farmers who are looking at the common good, that they're all sharing the same problem, is to develop a method to minimize the effects of these losses that are taking place. The best way, of course, from a hydrologic standpoint is to build a computer model, put a ground and determine what the groundwater is from a three-dimensional standpoint in there, and by simulation and then optimization, one can go in and say, how many wells do we need, what pumping can we have, where do we put the new wells, where do we take out wells, and things of this sort. You learn how to manage and get the most benefit you can out of it without causing greater losses downstream. But this is this tugging I was talking about, a one thing tying with everything else, because here you've got a very important, very valuable agricultural resource. You've also got very important metropolitan areas on downstream, and both of these need water. They're both using it for beneficial purposes, but there isn't enough water for everybody. And so this is a classic problem that we're running into, and the Solomon River is just an illustration of that. Another one closer to home is, again, going back to the Mojave area. The Mojave Water Agency, which is in Apple Valley, is faced with the problem of allocating water down there in terms of development and wells. This has gotten into legal problems, and I don't want to get into that now, but basically the problem is how to manage how much water each rancher or farmer can take out, as well as the municipal areas. And what's happened there, of course, is that the Mojave River drains down from the San Bernardino Mountains running north into the desert area. It's a very permeable alluvial material. The river typically has always been intermittent. In a wet year, it'll flow for a long distance going on down into finally end up in salt flats, and other years why it disappears almost immediately. But with the development of urbanization, particularly in Victorville and Apple Valley, you've got large bedroom communities with people commuting back and forth into the greater Los Angeles area, and the water table, of course, has gone down. Well, if the water table goes down, the river, which has been supplied partly by the groundwater when it was higher, is now gone, and so you get down to Barstow, which is another 40 miles downstream, and Barstow doesn't have any water. So it's the same thing, the Solomon River, except it involves a completely different situation. It isn't all irrigation development, but it represents the same thing of a competition for water taking place. What's being done there is, of course, efforts to try to manage this as much as possible, and the big thing that is hopefully a saving grace here is that the Mojave Water Agency is receiving water from the State Water Plan, which is taken down, brought into that area, and there are now plans for construction of a pipeline to take water coming into that area, take it down by pipeline to the Barstow area to be recharged and developed in that area. So again, we need more water in order to meet all the demands that are taking place at that particular location. Other areas, we've been talking about inland areas, but there are also what we call coastal problems, and managing them represents a slightly different set of circumstances. I'm sure all of you have heard of the concept seawater intrusion. If you have groundwater draining in a coast coming down to the ocean, typically the groundwater comes down and discharges in the beach face or underneath the beach someplace out into the ocean. But if you lower your water table, which has happened in many places in the coast in this country and abroad, you get it below sea level, and the sea level is up here, and so the sea level comes in and moves into the aquifer, and therefore you have saline water, and we can't make much use of saline water. More than 2% seawater just is almost unusable for us. So the question is, how do we handle something like this? This problem developed in Southern California, obviously right in the very beginning, because all of the orange groves and the Hollywood starlets we have came there because there was a good water supply. Not because of the river, but because many of the wells were artesian. The water came flowing out of the ground. It was a land of milk and honey, and everybody benefited. Of course, we stopped flowing almost immediately, and the wells have been going down ever since. By 1950, as much as on the west coast, the Santa Monica coast down to Palos Verdes, we had seawater in 2 miles in from the coast. And of course, wells would have to be abandoned in that area. So the question is, how do you stop this? Well, what has been done beginning in 1950 by the state was to try to build a barrier, a hydraulic barrier, to keep the seawater out. And what this involves essentially is putting in a line of injection wells, not pumping water out, but putting water into the ground through a well. And the wells are spaced, let's say every 500 feet, all the way along the coast from Santa Monica clear around to Newport Beach. And what happens there, of course, is that where you have this seawater and the fresh groundwater here, you build a barrier in between by building this up, because when you have an injection well, when you pump a well, the water level goes down. When you have an injection well, you create a mound. And so these mounds, if you have a line of them, tend to build a ridge of groundwater parallel to the coast. And so with the ridge built up, then some water from the ridge runs to the ocean, and the rest of it runs inland. Now you may say, well, we're wasting a lot of water to the ocean. Well, conceptually, that's true, except that if you know where the water levels are, which we do monitor them very carefully, you determine just how much you need. And all you want to do is to put up just enough to be a little bit higher than the sea, so that a little bit of the water runs this way, but most of it can run inland to where all the wells are pumping. And in the Los Angeles area, where this has been carefully measured, we're losing only about 10% to the ocean. And 90% is going inland as being redeveloped. In Orange County, treated wastewater is being treated and put into the ground to use for that fresh water to serve as these barriers and develop the additional supply. Another example of the coastal problem is the city of Honolulu. Many of you, I'm sure, are familiar with Waikiki Beach and all of the mobs of people that are over there in Oahu. And what happens here, of course, is that we get water from the volcanic slopes, very nice water coming out with tunnels going in, but there's still a tremendous amount of pumping right along the coast, just a quarter of a mile back from Waikiki Beach. You've got lines of wells stuck in there. And these wells, of course, are pumping water out, which is fresh water coming down from the highlands back of the wells themselves. But with fresh water and salt water, you've got different densities. And so fresh water in a coastal area is usually sitting on top of salt water. The difference of density is only about 2.5%, between 1 and 1.025. But it's enough to make a difference. And even though there may be mixing, it's not like oil and water. They do mix in what we call have a transition zone. But what you do have is fresh water up on top, and the wells, of course, are in the fresh water. They're not down in the bottom. But in the summertime, when you have all the tourists and the hot weather, you have a lot more pumping. And so the seasonal pumping goes up and goes down each summer. What happens, though, is that with this pumping that's going on, you begin to pump more, and you begin to pull up the salt water, rises up into the bottoms of the wells, what we call upconing. And as a result of this, you begin to move this water up into it, and you get a little bit of salt water. Not a lot, but coming in there. So the chloride content, which is what you get from seawater, it has a curve, goes up in the summer, down, and up in the summer and down. You got the same thing there. Clearly, the more you pump, the more that chloride gets up there. And if you get more than 500 parts per million, well, you're going to be out of business as a domestic water supply. So this is another problem. Again, how do you manage? What's the solution? Well, again, there isn't any nice simple answer, because you can't very well turn off the wells, which would obviously solve the problem nicely. But what has to be done here, again, is to look at the spacing of the wells, the location of wells, the pumping rate of the wells, and importations of water, which are now being done to bring water all the way around for the volcano around and bring it past Diamond Head and bring in new water into the area. So again, we're simply using more water than we have locally available, and we get into these transport problems, which become fairly costly. A final example, even closer to home in this coastal situation, is the situation down in the Artichoke Fields in Monterey Bay area. I'm sure many of you have seen them down the Castroville area. You have all this area, the Indus Basin coming out, and it's filled with these artichokes. They're all being irrigated, of course, by local wells. When these well fields started, I I don't even know when they started, but there was early part of the last century. The obvious thing was to take water from the water that was coming down the Salinas Basin in there. And so wells were put in this area. The first wells went into what was called the 180-foot aquifer. It was 180 feet down to the nice, good, permeable, sandy material in there. And this water was pumped out and the artichokes began growing. What happened, of course, was that you're right at sea level in that area, and water coming in from the beach right by Fort Ord in that area began to move in through there, and suddenly we began to get brackish water. So this wasn't going to work. So the next solution there, this is not management, this is mismanagement, was to say, we've got another aquifer, the 400-foot aquifer, down a little bit deeper. And so wells were put down there, and that has become the major aquifer now. Well, that was good, beautiful fresh water, but it also is pulling in water and doing the same thing. And so today we have the 900-foot aquifer where the newest wells are going in there. Obviously, this is not the way we want to manage the resource. What has to be done and what is being done is to, first of all, develop some other supplemental supply without increasing the pumpage that's going on in the area. And one of the things to do on that is to take treated wastewater from the city of Salinas, which is being done at the present time, to bring that down for irrigation purposes. And then the other alternative, of course, is to build pipelines from on up valley, up by King City in that area, to bring water down and bring it in as a supplemental source for irrigation in that area. So again, this is a matter of transport, a matter of cost, and a matter of trying to optimize the demands which exceed the local supply in a particular area. Well, finally, I think I've given enough illustrations here. Let me just say, where do we go in terms of the future? Well, I think what I've already said makes that fairly obvious. The demand for groundwater is steadily increasing based on population and competition and the lack of surface water. And so that's an ongoing factor. The second one is that this means there's more competition for water, and the illustrations that I've given here show you the kind of things we're running into. Thirdly, that's meaning there's more regulatory control, and that's something that is basically good and necessary. The idea has been all along here in California is to have the control of groundwater done at the lowest governmental level. We don't want the state looking over our shoulder and say, you've got to do this, you've got to do that in terms of your backyard well. What we want to do is to be able to operate as a unit. And so many of the hundreds of little water districts in little towns and villages and irrigation districts and so on are operating as management groups. And there has been legislation in the last 10 years, what we call AB 3030, Assembly Bill 3030, which authorized small water agencies to take control of their groundwater resources. And they simply had to look at what the resource was, evaluate it, what they were doing with it, what the potential was, what is the yield that's going to be available in the future, and to make plans for management accordingly. The similar things are happening now. You may have seen all the struggle with developers in Southern California. They are not being allowed to develop unless they can demonstrate a sustainable water supply into the future, which means they've got to have a well field that's going to work. And finally, the last thing under all this is that there is going to be more of what I'm calling management of groundwater by engineers, by geologists, by state and federal agencies working together to understand and work out what can be best done on this. You probably all know of the late Mark Reisner, who wrote the marvelous book Cadillac Desert. He pointed out years ago that we were going to be running out of water one of these days, and he certainly has done a good job in making that very clear. It was a very prescient statement when it first came out. But the problem really is that we tend to think of groundwater as a renewable resource. It's not like coal or oil or gas or something like that. It is renewable theoretically, and it is the catchword now is sustainability. It is sustainable, but I would put a big if underneath that, and that if is only if we can manage it properly, because otherwise we can destroy the resource and we can end up without enough water. So basically what I would say is that we've used a lot of our aquifers, we're using more of them all the time, and basically what's happening with all this is that they're beginning to wear out. It's sort of like, what, cars, houses, human bodies. They all need maintenance. They all need attention. They all need care. And if we could do that, we could maintain our groundwater. Thank you.
Ample time for questions and comments, so please.
When in the Fort Ord area,
Speak louder.
In the Fort Ord area, when they started drilling deeper to the lower aquifers, Monterey,
Yes.
did the upper aquifers, the salinity level drop over time and stop pumping?
It's my understanding that if you're working in sort of like sandwiches. You've got a nice sand layer, another sand layer, and a sand layer, and then you've got silts and clays in between, because these are alluvial outwash that's developed in there. If you turn off your pumps in the upper zone, then you're going to get salt, your fresh water moving back in, and you will improve the salinity. It's the pumping that is pulling it in. So that moving down below, there may be some small vertical connection, but not very much, because the permeability horizontally is probably 100 times better than what it is vertically between those zones. So that I would think that with turning it off and the abandonment of the shallow ones was why they did go there, because they needed more fresh water.
Professor Sachs is here, so I won't ask you for a legal opinion, but could you maybe just comment on the technical aspects of managing groundwater in an aquifer versus underflow of the stream and sort of the bed and bank concept?
I think that's a loaded question. What we're referring to is a problem that the state is facing right now as to what is groundwater and what is surface water. And it has practical ramifications from a water supply standpoint. Basically, a stream is fed by a water table that's draining into it, and the water is groundwater outside, and when it gets to the stream, it's surface water. But there have been considerations that if you have a well that's, let's say, just 20 feet away from a stream or something like that, and you begin to pump that well, are you pumping groundwater or are you really pulling in surface water? And one of the obvious ways of telling it, for example, is that often surface water, of course, with stream flow and rapids and everything, you'll have turbid water. And normally groundwater is very pure, very clean, because it's naturally filtered going through the sands. So if you begin to pump a turbid zone in there, then you say, well, that's surface water. And so now there are suggestions, I guess, that are under consideration that you will set aside a certain corridor on each side of the stream, and you will call that water surface water, whether you and I think of it as surface water or not. So I don't want to go beyond that particular point. Yes?
You're talking quantitatively about groundwater all the way through. What is the experience in these recharge projects with quality?
Putting water into the ground? Question is, what about quality of water? To put water into the ground right now, obviously the best water should go in that you can possibly get. What it amounts to is that you use the water that's available in most cases. In terms of, let's say, in Orange County, for example, because I happen to be familiar with that particular one, the treated water is drinkable quality water that's injected back in there. They're actually using desalinization on some of that water to develop it in there. But the water that's coming down the Santa Ana River is not treated. That's just water that's taken out and is put into a pond and let soaked into the ground. By and large, the natural filtration takes place of the water, of anything that's in there. We, of course, are looking always for viruses, and we're looking for various chemicals that may be there, particularly organics, because that's been such a contamination problem in the last 20 years. But by and large, most of the water is coming out very well. The problem that Orange County has, to be very honest about it, is that there are 14 different treatment plants on up the river, all the way up to San Bernardino, and all of them put their treated water back into the river, so that the water that Orange County gets is 60% wastewater. And of course, everyone is worried about that, and the Orange County Water District has been very careful to check and monitor their wells very well. But by and large, there has not been a serious problem. A lot of work has been done actually here with the Lawrence Berkeley lab with regard to tracing groundwater flows down there and following it. And we can find where this water moves in 1 year, 2 years, 5 years, 10 years as it moves on down, and check to make sure that the quality is there. By and large, nobody is putting poor quality water in, and the state health department is leaning over backwards to make sure that water is going into the ground that's going to be used by potable supplies immediately downstream must have a lot of criteria. It must go certain layer of sands, it must travel a certain distance, it must be underground for a certain period, it must be diluted with a certain amount of water so that what you're getting is usable water. For irrigation, for irrigation of urban areas, whether it's parks or cemeteries or golf courses or something like that, you can use poorer quality water. Yes?
You talked about a string of projects there with the Colorado river water and building up groundwater storage. And Cadiz was mentioned. And, you know, I don't know much about this, but the recharge rate was, to make the project viable, was exaggerated by a factor of 15 or something like that. And what's the relationship between the particular Cadiz project and these lower projects on that canal?
Well,
Repeat the questions to that.
all right. The question is about the Cadiz project, one of the ones of Metropolitan Water District of putting water into the ground from the Colorado River Aqueduct. Cadiz project has gotten a lot of publicity. It's the only one that has because of concerns, because the U.S. Geological Survey criticized the report, I believe initially because they said that it would not be representative. The problem that comes up here is that what we're trying to do, or what they are trying, I'm not involved in it, what they're trying to do is to put water into the ground to build up a reservoir. But the question is, obviously there's water under the whole Mojave area right now, and you can go down and put it in there. But if you take this and you pull your limits that I'm talking about, we want to build it up and take it back down in this area. But you can also put your wells down and take this water here. And so the concern is that we may actually have adverse effects because we're lowering the water table in other areas where it's feeding and supplying other things that may be quite a long distance away. So there's a lot of effort being made to make sure that the design and operation of these is going to be successful. I don't know personally about the Cadiz project, what's happening there, but I do know the Metropolitan Water District is moving ahead with development plans in that area for these various ones. I think it's got a great potential myself, but it has to be properly done. Way up in the back.
Going to be a lot of groundwater transfer in the future, even though it is legally allowed right now.
You mean to take groundwater out and move it to someplace else?
To either be moving it or to substitute, to use groundwater to substitute for surface water transfer.
Well, we do have part of the regulatory picture that I mentioned right at the end is taking place. There's a lot of effort being made to make sure that we do not take water away from wells that are in there. And urban water management plans, for example, are now required throughout the state so that you must show that there is adequate water that's going to meet there, and based upon your development and your planning and your population projections, that that water will be available at some time in the future. The main concern that I've always worried about is the quality itself. And if the quality is there, there should not be any problem. Yes, sir.
How deep are the deepest wells in California, and how deep do you usually get water? And is the limit our ability to pump, or the limit that there isn't water?
It's where the water is. You can pump almost anything. The deepest wells I know of are down in Kern County. They're about 2,000 feet deep. basically almost everything, like in the Central Valley and so forth. You've got fresh water, but down deep you've got very old water, which geologically is old. We call it conic water. It's water that's essentially been there for a very long period of time. And because it's been there in contact with rocks, salt water is dissolved from the rocks, and because it's not flushed out, it's moving very, very slowly, why you have a poor quality water. So that if you go, for example, Stockton, right in the middle of the valley, for example, you go down more than 600 or 800 feet, you're going to get poor quality water. So if you stay up in the upper few hundred feet, well, you're in good shape. That water is going to be there, there's no point pumping it out, and it's going to be, say, either brackish on down below that. So your depth of a well depends, of course, on what the local conditions are. Yes, David.
With the implementation of the AB 3030 program, there resulted encouragement of groundwater management within the local districts. But there's been a wide range of plans developed as a result of that. So I was just wondering, what your opinion is about ways that process might be improved. I.e., are there districts that have broad guidance, but there might be things that they think they're doing to manage the groundwater, but maybe there's things that they're entirely missing?
Well, that's a difficult question to answer.
Could you repeat the question?
Yes. The question here was about AB 3030, which dates back to what, 1992, I think is when it started, which is a law that says that I mentioned very briefly, that districts can take control of their groundwater by developing what's called an AB 3030 plan, which is submitted to the Department of Water Resources in Sacramento, is reviewed, and then approved. And if it's approved, and there have been a few hundred of them now, I believe, that have been done in the state, this allows the local water district to take control of its water supply. And by that means that it can determine how the wells are going to be developed, how the wells are going to be managed, how they're going to be pumped, limitations, if any, on new wells. All of those things can be done by the local district and the entity that's there. The concept is very good, and obviously it serves a very useful purpose. The question is it being used correctly all the time? And to be very honest, I don't know the answer to that. My experience with reading several of these reports and studies that have been done, I think it's a very good thing, and I haven't seen any misuse of it to any particular point. It doesn't solve all the problems because you still have so many hydrologic problems, for better or worse, are technical hydrology and also our socio-political problems. And so you get into a situation where you're trying to trade off development of new wells for land or wetlands or something like this, and as a result you run into all kinds of problems in trying to make it work. But the idea is, I think the best thing about it is that it's made an awareness of groundwater management, and that's what I was saying. It's become so important here because we've begun to realize that this is a resource. It's sitting, all these 1/3 of a million gallons that I had under our feet here are still sitting down there, slowly moving, and we can make good use of that, and all we have to do is be aware of it. It's not easy. As I said, it's an unwieldy reservoir to work with, but it can be done, and we've learned a great deal about it. The whole field of computer modeling of groundwater is a tremendous field in itself, which is a whole other subject, but we do have possibility for thousands of areas like the Solomon River. You can build an aquifer model for that and find out what is the optimal way of running that particular basin. There are limits, obviously, and what we try to do is to find out what they are and make them work. That's not a very good answer, but it's indirectly.
Question. I have a question.
Yes.
Looks like other western states like Arizona and New Mexico, Nebraska, they are in the recent past have gone towards classifying their state into natural resource districts, which are based more on watersheds and physiographic boundaries and groundwater, surface water basins. We don't have. Do you think that California should be headed in the direction of, for purposes of conjunctive management of surface water and groundwater in intelligent ways, should we go more along the lines of flow of water so that we manage water in terms of these basins so that we take better advantage of the nature of the attributes of water than political or administrative boundaries?
Well, the answer is obviously yes, because, I mean, clearly if we can do it in terms of a hydrologic boundary, it makes a lot more sense than having a grid of, let's say, square counties or something like that, putting them in there. It's a matter partly of practicality. I mean, I've seen some districts which are done strictly on a political basis, but they're not far off of the true hydrologic boundary that's taking place, because it may be difficult. Take the Solomon River, which is a big, long, sort of a banana-shaped basin draining to the east. Why, it may be very hard to actually put all that into pieces in there, because you're going to break up city boundaries and county boundaries and things of that sort. But conceptually, that makes a great deal of sense. Whether we need more of these districts here is, I think, remains to be seen. Right now, I think with what we're doing on these small groups and small districts that are operating, which may be only, you know, 5 by 10 miles or something like that, if it is something that makes sense so that you have basically control of most of the resource, it's a small valley, for example, and you can see across it very easily, then developing that as a unit makes a great deal of sense.
I know there's a good deal of concern about the quality of water that you're putting into the groundwater. I'm wondering if there are any issues with sort of a reverse situation where there being things in the ground, say like arsenic, something that's naturally occurring in the soil or the rocks that would contaminate the water that you're putting into the groundwater?
You mean water that you're taking out of the ground would have these present in there?
So you're taking your treated water and putting it in, and then there's something
Already down there.
Right.
Well, the whole field of groundwater contamination, both natural and man-made, is very obvious. I mean, sure, all of you have heard of MTBE, I think, at the present time, chromium-6, chlorate. All of these things are new chemicals in the last 10 years that have suddenly emerged, and we find out, oh, if we drink 2 parts per billion, it may be toxic after 50 years or something like that. So we are concerned about how to maintain a quality control. By and large, there are a lot of places where you would not be allowed to pump water out of the ground and put it back in again because it would not be acceptable. That's maybe facetious, but that's literally what's happened in terms of what's being done. The contamination standpoint from municipal supplies and industrial supplies is, I think, pretty much under control now. We've seen all of them. We've all discovered every gas station has been found and cleaned up. And hopefully, and I say hopefully, most of those things are gone. So that there is an awareness that this resource has got to be protected. But there are problems. I mean, MTBE is a classic one because it moves very easily, it goes into solution easily, and it's very hard to get rid of. And you can't just go in and pump and pump and pump to try to treat it all in there. But there's, everybody is working very hard. The state health department people are very, very adamant about what goes into the ground every place. And clearly if there's contamination there, you're not going to put good water after bad. That's important.
Yes, yeah. You have mentioned previously the question of wetlands. That brings to my mind the idea of the frequent conflicts here between groundwater development and ecological impacts. First, how is this solved? For instance, with the AB 3030, theoretically the local power is the power, but they cannot override another regulation with the California State Department of Conservation or Fish and Wildlife. And also, are there well-known cases of conflicts between groundwater development and conservation of wetlands or some other case of landscape?
Well, wetlands are a special case. The policy right now of certainly everybody in the United States is to preserve them. You may be able to trade wetlands one place or another, that sometimes happens. But what it amounts to, of course, is that a wetland represents a point where you've got a controlled water table. And so this means that you can't go in and dewater that and pull it down 20 or 30 or 50 feet in there. So it becomes an area that has to be set aside. Often, of course, here in the coastal area, why the wetlands are brackish or saline water because they're in contact with the sea. And so we're not pumping that water anyway because it's there, and that can be protected. But you've got habitat problems in inland areas for ducks and things like that, and a great deal is being done these days to try to manage that. The best example I know indirectly of is rice fields in northern Sacramento Valley. Here, by flooding these fields, you're providing a chance for water to leach out, but you're also providing habitat for ducks and migrating birds going through there. So much can be done with coordination between these ecological needs and the agricultural needs to benefit both parties, if it were.
Any more questions? I just want to tell you one. Go ahead.
I'm curious on the aquifer storage and recovery kinds of projects. If the permitting agency is now in the process of reviewing not only whether the aquifer itself, it has a quality of a certain level, or the water that's being injected, if that were potable, but that water has different conditions attached to it that would change the environment in which you're injecting it. So if you're going to potentially change redox conditions and then possibly mobilize natural contaminants, let's say arsenic, for example, if they're looking at that level of technical detail.
Well, let me say I hope so. I think by and large any of the aquifer storage and recharge, these are wells, we call them ASR, aquifer storage and recharge wells, where you can put water in or take it out. You do artificial recharge, putting it in, you can turn around and pump the water back out again. Because the water goes down, it simply spreads out, you pump it, you pull it back in, and it goes up again. And so what you want to do, of course, is to maintain the potable quality that hopefully exists there by what you're putting in. And the question that this young woman is asking here is whether if you put in slightly different chemical mix in water, because obviously waters do have different salt concentrations, whether that would cause some chemical reaction which may activate something in terms of, let's say, a chromium or an arsenic would be the obvious things that we'd be worried about. And I think that we hopefully know enough about geochemistry to be able to be aware of what these problems are, make sure we don't do it, because most of the wells that I've seen going in are very carefully researched in terms of what exists down there, what the water's going in, how it's going to be handled. So I feel good about it.
I had heard from some geological survey people that there is really serious concern about that problem in a couple of the Southern California projects. I mean, that it's not something that people could feel comfortable about.
Well, that may very well be. I mean, I don't know details of things on that particularly, but any of the projects that I've read about, why they seem to be very concerned about the quality. And at least like in Orange County, for example, the quality is an extremely important thing. We've got, there's many things, just like nitrate, which is a simple thing, but there's an awful lot of nitrate in Southern California. And we think, well, we don't worry about it. Well, it doesn't take very much to get up above a limit of 10, and then you've got problems on your hands. And so this is an ongoing question. What do you do about an aquifer? San Gabriel Valley has got lots of nitrate in it, and this is a major water supply for 1 million people. So the question is, you've got to be very careful of what water you're pumping, how you're mixing it with imported water, and so on to deliver a quality that's acceptable. I think we've exhausted them.
I just brought the end up is the Berkeley connection. It'll be a nice Berkeley connection. Professor Todd mentioned about artificial recharge and also mentioned the salt accumulation problem because of poor drainage in the Indus Valley. It turns out that Hilgard, of whom we have the Hilgard Hall name,
yes,
as far back as 1880, he wrote a report to the president of the University of California, drawing upon the drainage problem in the Indus Valley.
Is that right?
And then he said that in San Joaquin Valley, we are going to have the same problem. That's a very famous report. And in about early 1900, Eugene Hilgard suggested in Bernardino County for the first time of artificial recharge, which was implemented in the early 1910 or 1912. Over 2 successive years, they were able to increase storage by something like 15,000 acre feet. So Hilgard in this campus, who was supposed to be a soil scientist, actually pioneered groundwater. With that, let me stop and thank Professor.
Good.